The idea behind multi-programming is to keep the CPU busy with the processes at all times, maximizing its utilization. We try to avoid idle times in CPU, in other words. In a system with a single processor, only one process can run at a time. If there are multiple processes waiting to run, they have to wait until the CPU becomes available, and then they can take their turn. Okay? So quickly switching the CPU between processes allows users to interact with each program while it runs. To achieve these goals, the process scheduler selects one available process to run on the CPU. So when a new process created, they are added to a job queue, which includes all processes in the system. Processes that are ready to run are placed in a list called ready queue. Okay, ready queue. And this is usually organized as a linked list. The ready queue has a header that points to the first and last, to the first and the last process. In the list, and each process in the ready queue represented as a process control block has a pointer to next process in the ready queue. Okay. So process scheduling is often represented using a queuing diagram, like the one in this figure. Imagine each process as a box, and there are two main kind of boxes, those in the ready queue and others waiting in device queues. The list of processes waiting for a specific input-output device is called a device queue. In fact, each device in the system has its own queue for processes waiting to use it. Okay, so the circles in the diagram represent resources that help these processes, and the arrows show how processes move through the system. When a new process starts, it joins the ready queue first. Okay, it waits there until it's chosen to run or dispatched. While this process is running, several things could happen. Like the process might ask for data, okay, from a device and join a queue for that device, or it might create a new process. It might fork a child process and wait for that new process to finish, or it could be interrupted and forced out of the CPU, returning to ready queue. Okay, so they are returned to ready queue after all these operations. But in these cases, you can see that the process eventually goes from the waiting queue back to the ready queue. Okay, this cycle continues until the process finish its task. When that happens, okay, it leaves all queues and its information is cleared and the resources it was using are freed up. As you see, a process migrates among scheduling queues throughout its lifetime. So the operating system must select processes from these queues in some fashion. Okay, so the selection is carried out by the appropriate schedulers. In operating systems, there are 3 different types of schedulers that manage processes at various stages of their execution. Let me explain them. So the long-term scheduler, as also known as a job scheduler, plays an important role in determining which programs or processes are admitted into the system for processing. It controls the degree of multi-programming, which refers to the number of processes residing in the system's memory. If more processes are admitted, it reduces the likelihood of processes being blocked, ensuring better CPU utilization. And the long-term scheduler carefully selects processes based on various factors, such as the process's I/O and CPU bound characteristic, I/O bound and CPU bound characteristic. Its primary goal is to maintain a balanced mix of processor bound and I/O bound process. Okay. The short-term scheduler is also known as the CPU scheduler. is responsible for selecting the next process from the ready queue for execution. So it allocates the CPU to the chosen process, making sure the CPU is utilized efficiently. This scheduler needs to operate quickly and frequently, often within milliseconds, and it selects processes for execution based on various events, such as clock interrupts, I/O interrupts, system calls, and signals. Okay, so its efficiency is crucial to prevent CPU idle time and ensure prompt response to user interactions. Okay. So the medium-term scheduler acts as an intermediate level of scheduling in some systems. Its primary function is to manage the degree of multiprogramming by swapping processes in and out of the main memory. Okay, swapping. When memory becomes a scarce resource due to a large number of processes, the medium-term scheduler can temporarily remove processes from memory and later rebring them for execution. This process known as swapping. Okay, so it helps optimize the utilization of available memory and ensures that active processes have sufficient memory space for execution. Actually, each scheduler plays an important role in ensuring efficient process management, resource utilization, and system responsiveness in an operating system environment. Lastly, I want to talk about what a context switch is. Okay, so a context switch is like changing the focus of your attention from one task to another. Imagine you are working on a computer, typing a document, and suddenly you receive a notification. You click on the notification to read the message. When you go back to your document, your computer has to remember where you left off, the words you typed, and all the other things you were doing. Okay, in the computer world, something similar happens. When you are using a computer, the operating system might need to pause, okay, what you are currently doing, and switch to a different task, like handling an incoming message or running another program. During this switch, the operating system saves all the important information about what we are doing, like the state of processor, the status of the memory, and other necessary details. This process of saving the current state, pausing the ongoing task, and then resuming the new task is what we call a context switch. It's like the computer's way of multitasking, allowing it to juggle different tasks smoothly. Okay. However, this context switch takes some time, and it is considered an overhead because the computer isn't doing any useful work during this moment, during context switching. Okay, the speed of the switch depends on the computer's hardware, like how fast its memory is and how many details need to be saved and restored. Some computers have special features that make the switching process faster, while others might take a bit more time.